I'm Matthew Sandoval, and this is Lab 4, Bar Magnets. The 5 parts of this lab are the introduction, experiment, code, discussions, and conclusions. The purpose of this lab is to measure, using the correct fundamental physical principles, the on- and off-axis magnetic fields of a bar magnet. The next purpose is to construct a computational model of the magnetic fields and compare the observed and simulated results. The main fundamental physical principle and model used for this lab is the Biot-Savart law. This law correlates the magnetic field to the current in a particular object at some observation point. This law allows us to quantify the magnetic field for a section of said object using the below formula. This formula is powerful, allowing us to derive many related formulas that not only are fundamental for this lab, but for physics in general. Following formulas are the magnetic field when the distance is far from the loop, the magnetic dipole moment, the on-axis magnetic dipole field, the off-axis magnetic dipole field, which an important thing to note here is that the direction of the off-axis magnetic dipole field opposes the magnetic dipole moment, and finally the magnetic field in general due to a bar magnet. A brief preview of the results can be found at the bottom of this slide, noting the magnetic dipole moment, the observed off-axis field, the computational off-axis field, and then also the conclusion that the magnetic field grows stronger as proximity increases. I'll now explain the procedure of this experiment. The first step was to compensate for the magnetic north and set up the experimental setting. The first 2 images on the left of the slide depict this. The next 2 images, which correspond to a real-life image and the image in the lab document, correspond to the second step, which was to locate the magnetometer in a cell phone. Once both of these key setup steps were completed, I then had to follow a lab document and record measurements as needed. These measurements were the distance between the magnet and magnetometer on axis when the x component of the magnetic field read 20t, 70t, 120t, 170t, and 220t respectively. I then had to do another 3 measurements, but this time it was with the off-axis, when the net value of the magnetic field read 100t. Still following the lab document and having taken these measurements and put them into the corresponding Excel sheet, I then completed required calculations as indicated. I then utilized this Excel spreadsheet in order to create a computational model that would predict the magnetic field. I then compared the results and made necessary conclusions and answered supplemental questions. The bottom 4 images on the left side of the slide show setting up and finding the off-axis measurements. The initial conditions for this experiment are listed below. The system was the magnetometer, which was the cell phone, and the surrounding of this experiment were the bar magnet. Note, we had to assume that nearby electrical equipment and interfering magnetic fields, aka Earth's field, did not exist, nor did they affect the results of the data. We also had to assume that the bar magnet was essentially a magnetic dipole. A model related to this experiment can be shown, which is the magnetic field of a bar magnet, which is also the magnetic field of a magnetic dipole. Here are my observations and the results of my data collection. Below is a screenshot of my Excel spreadsheet, including where I inputted data for the following measurements: R20, R70, R120, R170, and R220. And below that is where I inputted the values for the off-axis measurement. The Excel spreadsheet automatically created the distance versus magnitude of magnetic field slope line. And you can tell from the graph that it shows an increasing magnitude of magnetic field, which was the y-axis, as the distance, which was the x-axis, decreases. Again, after collecting necessary data and inputting it into the Excel spreadsheet, I had to do a couple of calculations as per the lab document. Using a formula equivalent to the graph's line data, we can solve for k. The formula is shown to the left, and it's one of the formulas mentioned in the introduction. K can then be substituted into the proper formula, which again was shown and explained in the introduction, in order to derive the observed magnetic dipole moment. Some more calculations I had to complete were for the off-axis measurements, where we needed to remove Earth's magnetic field from our data. This was because Earth was not included in our system, and this would make it the magnetic field more accurate for just the magnetic dipole. An important thing to note is that the magnetic dipole moment is denoted by the symbol mu. The first step of the computational model was to input initial conditions. So the basis of the code that we were given, so the example, gave us the standard values for mu naught and the size of the bar magnet. And then the next initial condition value I had to input was the magnetic dipole moment, or mu. I then translated the formula for the magnetic field into a computational rendition in order to computationally model the magnetic field using the derived value of mu. Once those initial conditions were inputted, all that was left was to model the arrows of the magnetic field that would be created based on the magnetic field that was calculated. The last chunk of code has to create the off-axis magnetic field arrows. Here are a few images of the results of my computational model, including the off-axis, on-axis, and perpendicular arrows in the respective colors. The most important value to note here is the final vector, b at 45 degree at distance d. That is the simulated off-axis magnetic field value, and taking the magnitude of this is what I used that corresponds to the back end of my preview of the computational off-axis field. So now to kind of digest some of the results and compare, the first thing I want to reiterate, a recap of the experimental observations. So the one important thing to note is the magnitude of the magnetic field increases as the distance of the magnetometer to the bar magnet decreases. The next result is the magnetic dipole moment, which was calculated based on the observed values. This value is different to what was to be expected, and this could be due to a number of errors, which I will go into later. So taking the magnitude of the B net average gave me the experimental magnetic field for the off-axis. Then taking that vector, which I mentioned in the results of my computational model slide, and calculating the magnitude of that, that gave me the magnetic field for the off-axis in the computational model. So because of the significant differences in the observed and computational values, there are a couple errors that may call into question the exactness of this experiment. These errors can include nearby electrical equipment, accidentally bumping the smartphone, failing to line up the smartphone with the north before starting, steel or iron objects near the smartphone, finding the incorrect location of the magnetometer, faulty phone equipment, and human errors So to conclude this lab, there's two important what-if questions that we need to answer. What if you hadn't oriented your experiment to compensate for the magnetic north? How would your results have changed? So the measured results would be significantly different. The magnetic north interference, it would alter both the X and Y components. The Z component, however, would have no interference due to the nature of how the measurements were taken. And the final important question that we need to address is, what if you were to stick two identical magnets together? So adding a second magnet would increase the magnitude of the magnetic field. Theoretically, this would double the value because there's two magnets, and because the magnetic field would be stronger, the required distances in order to achieve the same magnitude level of magnetic field would decrease, which again would change the results of our observations, our calculations, and computational models.